Okay, I'll try to not to go over time too much so that you have a non-zero break in 1 hour. Okay, so okay, so what I would like to so the plan for today is really in 2 parts. So first of all, I want to finish the part on scaling limits of random maps, and you know, so far I think I've given you some indications of how you you know, you can start studying the problem of scaling limit for random quadrangulations and constructing a limiting object. So what we did so far, okay, is that we really proved that up to extraction, if you renormalize graph distances in a uniform quadrangulation, then this converges to a limiting metric space SD. So this is really up to extraction in a distribution in the Gromov-Hausdorff sense. Okay. And last time we stated and proved a couple of properties that have to be satisfied by the limit. And at the very end, I told you actually what the limit is. Okay, how you can actually obtain this limit as a function of processes, stochastic processes that you know well, which are the Brownian excursion and the label processes on the Brownian tree, and therefore deduce that the limit is unique and does not need to pass through extractions. Okay, so recall. So we stated that almost surely D is equal to D star, where so D star is really a function defined in terms of the process E and Z, which is the infimum of the sums of dz distances between points Si and Ti for I ranging from 1 to k, where k is an arbitrary integer bigger than 1, and S1, T1, Sk, Tk is an arbitrary family of points in 0, 1, such that the dE distance between Ti and Si plus 1 is equal to 0 for I between 1 and k minus 1. Okay. So again, I'm not going to prove this theorem. It's you know, it would take more than the 2 hours that remain here. However, I want to state some properties of the Brownian map that are, you know, if not implied, you know, that are related to this theorem. So, okay, so maybe note that this implies a convergence of VQN, which we normalize distance dQn to S D star in the Gromov-Hausdorff sense, and this without taking extractions. Okay, and this is really because it identifies the limit. Now, so what does that mean? Okay, so we see that D equals D star means a property that is rather curious. Tells you that if you take 2 points in the map, and of course you always have this a bit special point P of S star, which I called X star the last time. It takes really the role of the V star for the map. So you should think of it of being a uniform point chosen in the map. And to that point, we know all the we can construct all the geodesics. Okay, we know that the geodesics, which was in red last time, forms a kind of tree. Okay, and this tree we called it, if you like, TZ, the tree coded by Z. And you know, again, using the upper bound dz for the distance between S and T means that you just travel along this tree, okay, from, let's say, P of S, sorry, to P of T. Okay, so you just travel along this tree. Now, taking this infimum means again that you are allowed to take, in fact, intermediate points that correspond to points in which the tips of in the geodesic tree, the leaves actually in the geodesic tree coded by TZ are identified. Okay, so for instance, you can choose an intermediate point here, U and V, okay, such that PU is equal to P of V, and then take this second path, which maybe is a bit better. Okay, but then, you know, you can continue by taking sequences of arbitrary sequences of points, and it means that geodesics, you know, between, or at least a geodesic, let's say some geodesic, between P of S and P of T can be well approximated by a path made of pieces of geodesics to or away from X star. Okay, and of course, this is maybe a quite surprising property if you see it for the first time, because there is no reason at all a priori why this property should be true. Okay, for instance, if you take you know, the Euclidean plane and fix a point A, it is certainly not the case that a geodesic between let's say B and C is well approximated by pieces of geodesic from either A to, you know, either to A or to C. Okay, there is actually no way, even in a very weak sense, to approximate a straight line by using such paths. Okay, so it is a very curious property of the Brownian map, and it is linked to the following fact. So how should you picture the Brownian map? You should really imagine it as a, you know, as a very kind of spiky object, you know, a kind of, if you like, of tree-like object, in which so maybe X star is at the tip of one of these spikes. And the thing is that typical points in the map are really points that are located at the tips of these spikes. And when you take a geodesic from one of these points to X star, say, then the first thing you do is you go down in a very deep valley, okay, remain in that valley, and then at the very end go to the spike on the top of which X star is standing, okay? And the same for P of T, you somehow go down in a valley, and at some point these two valleys will merge, okay? So the idea is that the geodesics in the Brownian map, they look very much like paths in a mountain area. Okay, you have the tops of the mountains, and then you go down in valleys, and these valleys, you know, coalesce together, if you like. So this is really the kind of picture that you should have in mind. Okay. Okay. So. Okay, so I'll come to that again in a second. So some you know, properties of SD. Well, okay. From now on, I'm going to assume, okay, that this theorem is known, though we haven't proved it. But in this way, you know, we are talking about one single object, and I think it's better than having this idea of taking subsequences all the time. Okay. So a theorem, which is due to Le Gall and Paulin, tells you that almost surely SD is homeomorphic to the two sphere. Okay. So that means that this metric space is really a random surface. Okay, so in this sense, is really a random surface. But now you can ask about what the regularity of this random surface is. And the fact is that it's a very irregular random surface. Well, first of all, we have this, this idea of geodesic merging together. And certainly this is not a property that is satisfied by smooth manifolds. Okay? So it's really a very rough structure, and one way to measure this roughness is to compute the Hausdorff dimension. Okay. So another result by Le Gall says that almost surely the Hausdorff dimension of S is equal to 4. So I hope you have all seen Hausdorff dimensions at least once before. I'm not going to prove this theorem, but actually it's actually a good exercise show that so the so-called box counting dimension of SD, so which is okay, let's say the upper box counting dimension of SD, which is the lim sup as epsilon goes to 0 of the log of the number of balls needed to cover the space S divided by the log of epsilon. Okay, is less than or equal to 4 almost surely. Okay, so this property uses the fact that D is less than dz and the fact that Z is almost surely 1/4 minus epsilon, let's say 1/4 minus eta Hölder continuous. It's actually a very nice exercise, and it's a well-known fact that Hausdorff dimensions are bounded from above by the box counting dimensions. Okay, so this exercise at least gives you one of the directions there, and the lower bound comes from a finer study of the volume of balls in SD. So this roughly says that let's say for almost every x, okay, let's say for almost every t in 0, 1, if I look at the Lebesgue measure of the set of points S such that D between S and T is less than epsilon, so you should understand that as the volume of the ball of radius epsilon in the map, then this is of order epsilon to the 4 plus a little low of 1 as epsilon goes to 0. Okay, so the volume of small balls in the map is of order the radius to the power 4. Okay, and of course this is something that does not look at all like Euclidean geometry in 2 dimensions. And this is a way to quantify, if you like, the fact that typical points in the map stand at the tip of very thin spikes like this. Okay, the volume is really much smaller than it should be, would be if it was a smooth surface. So maybe I want to give an indication of the proof of this sphericity theorem. So there are actually two proofs in the literature. So the original proof by Le Gall and Paulin, and another one by myself. So they are quite different in spirit. The one by Le Gall and Paulin argues directly in the continuum. It does not use at all the fact, if you like, that SD is a limit of quadrangulations or of random maps, but only the properties of how it is built from the processes E and Z. And the alternative proof that I proposed, in fact, uses a lot the fact that this is obtained as a limit of discrete spaces. So I want to give an idea of the proof, the original proof by Le Gall and Paulin. So idea of proof of the sphericity theorem. And the idea is that it relies on a theorem by Moore. It's a very old theorem of the 20s about quotients of the sphere. So that says that let R be an equivalence relation on the sphere, which is closed. So it's a, if you like, it's a closed subset of the product S2 times S2. Well, it's closed and it's properly contained. Okay. So not all the points are identified by R, if you like, and such that every equivalence class A of R is connected as well as its complement. Okay? So I'll draw a picture in a second. Then the quotient space S2 over R is homeomorphic to S2. So what does that mean? So if you take the sphere S2, okay, then essentially, let's imagine first that you take an equivalent. What is an equivalence relation? Well, it's really a collection of points which are all identified together by R. Okay. Now let's imagine for a second that, well, if an equivalence relation, an equivalence class is a single point, then we are doing nothing. Okay, it's identified with no other point, so we are not doing anything. Now let's imagine, for instance, that one of the equivalence classes is a line, which means that we really want to pinch, if you like, this line into a single point. Then certainly if we do that, that should not change the topology of the sphere. Okay. What would change definitely the topology of the sphere was if one of the equivalence class was disconnecting the sphere into two parts. Because in this case, yes, in this case, it would mean that all the points on this circle are identified into a single point, and this single point would really disconnect the points that sit sort of inside of this circle and outside of this circle. Okay, it would mean that it sort of strangles the sphere into what is called a bouquet of two spheres. Okay, two spheres that touch on only one point. Okay, so you really want to avoid that. Okay, and another thing that you want to avoid, of course, is that you, for instance, you take 2 points that are away in the sphere and you identify them together. Okay, which would make so it's rather more difficult to do, but it's like a pinched sphere like that. Okay, and this is not a sphere because the neighborhood of this pinch point is not homomorphic to a disk. Okay, so you don't want to do that. So you want the equivalence classes along which you identify points to be indeed connected, but you also want the complement to be connected as well. Okay, and this is of course a very general theorem. So you can, for instance, consider some of the equivalence classes can have a non-empty interior, if you like. It doesn't really matter. Some of them can have an empty interior, and so on and so forth. So it's a theorem that is used a lot in dynamical systems in the theory of mating of polynomials. So, okay. So how can we use this theorem? So we actually need to use this in conjunction with the following result. So proposition, it holds, so almost surely, it holds that d of st is equal to 0 if and only if either dE of st is equal to 0 or dz of st is equal to 0. And if s is not equal to t, then only one of these two situations occurs. Okay? So certainly if s is equal to t, it's at distance 0 from itself, and all of this is true. But as soon as I consider two points that are identified, if you like, by a non-trivial equivalence class of the points identified by D, then it means that either they code the same point in the Brownian tree, or they code the same point in the Brownian Z exclusively. Okay? So let's maybe draw a little picture of what's happening. So recall that one way to look at the Brownian tree, so the Brownian tree is a quotient of the interval 0, 1 by a certain equivalence relation and with a certain metric. But of course, it's always the case that 0 is always identified with 1. Okay, so I can really see the Brownian tree as a quotient of S1, the circle S1, rather than 0, 1. Okay. And what does this equivalence relation work? Well, again, points that are identified for the Brownian tree are points that are facing each other, or whose images, if you like, are facing each other below the graph of the excursion. Okay. So on the circle, it means that I will identify, for instance, these 2 points, okay, if and only if all the values of the excursion on this arc are bigger than the common value taken at these 2 points. Okay. So in fact, it's convenient to represent the equivalence classes or the identified points in the tree by a diagram made of chords inside the unit circle like this. Okay? And you will note that, so most of the time, the equivalence classes are made of only 2 points, okay, because of properties of Brownian motion. Okay? If you typically, an excursion of Brownian motion above a certain level will look something like that. It will immediately after the end and before the beginning of the excursion take smaller values. So only 2 points are identified there. But every once in a while, you encounter a local minimum, and this one certainly is identified with exactly 2 other points. Okay? So in this case, you have equivalence classes that look like triangles like that. Okay? If you like. This corresponds to the red triangle there. Okay, so we view the set TE as a chord diagram in the unit disk D, by linking identified points with, you know, for instance, a chord. And on this picture, what I indicated is that this chord can be, for instance, an arc of circle, like a geodesic in the hyperbolic disk. It's sometimes convenient to do this, and it actually gives also a much nicer picture. But you can take a straight arc if you like. So more precisely, you know, I can get that TE, the CRT, can be viewed really as D quotiented by an equivalence relation E. So where where the classes of E are you know, either points in the boundary of D, okay, which are the points which are not identified with any other point, okay, or chords in you know, in D bar between how should I say that? You know, corresponding to equivalence classes for D equals 0 with two elements. Okay, this really corresponds to pairs of points facing each other, or let's say geodesic, you know, ideal triangles in D bar corresponding to the equivalence classes with 3 elements. Okay, which means that if I have 3 points that are identified together, I really want to consider the equivalence class of this extended equivalence relation as the filled up triangle and not only the boundary. Okay? If I do that, then what I obtain is that this is a closed equivalence relation on D, or actually on D bar, with whose equivalence classes are connected, and with connected, okay, so not yet with connected complement. So what I want to say, really want to say that they are simply connected, if you like. Okay. Okay, so for now, let me just state this fact. You will see in a second why I have to fill up the triangles. Now, what we can do is do exactly the same for Tz. Okay, Tz, we can also view it as a certain quotient of the disk by an equivalence relation tilde z, which is defined in exactly the same way. Okay, so something that is not obvious from the start is that Z also, you know, identifies no more than 3 points on the line. This is actually not, strictly speaking, needed for the argument that is here, but it's a fact, and actually it's you know, nothing more complicated happens than in the previous picture. Okay, so I'm going to skip this this fact to sweep this fact under the rug, and now. Then we can see S, which, as I recall, is 0, 1, quotiented by D equals 0. We can, in fact, see it in the following way. we can see it as S2 quotiented by the union of E union Z, where tilde E is now seen as an equivalence relation on the northern hemisphere, and tilde Z is seen as an equivalence relation on the southern hemisphere. Okay, if you like, the northern hemisphere is nothing but a disk topologically. So I can identify it with the disk, the unit disk. And on top of this disk, I have my identified points. Okay. So if you like, here I have, for instance, some chords that are drawn there and some ideal triangles drawn there. And at the southern hemisphere, the same holds. Okay, so I have maybe this chord and that chord, and so on and so forth. Okay, so this corresponds to, if you like, to Z, and this corresponds to E. Okay. And in fact, this picture, we sort of have seen a similar picture before. If you remember when we considered the property of the Schaeffer bijection, so what did we do in the Schaeffer bijection? You know, when we wanted to show that the arcs from a vertex to its successor do not cross, what we did was we first unfolded the tree of the Schaeffer bijection into a polygon, and then we reasoned on the outside of this polygon. Okay, so we drew the arcs outside of the polygon in that way, by keeping in mind the fact that, okay, so maybe this would be the blue arcs now, by keeping in mind that the polygon itself has to be folded on itself in a tree-like fashion. Okay, and this picture is in fact exactly similar to that one. Okay, you should imagine this polygon as being now the unit disk. Okay, we are really looking at the Brownian tree as a quotient of the unit disk, just as we saw plane trees as quotients of polygons. And on the outside, we have, if you like, the identifications given by the tree coded by Z, the tree of geodesics. Okay. Okay, so this is reminiscent of Corey-Vauquelin-Schaeffer bijection. And now, at this point, I want to use this proposition, okay? Because I know that points that are identified through D, okay, well, are points that are either identified by the blue, by this equivalence relation, or the other one, and both of them cannot happen simultaneously. So what does that mean? Well, it means, in particular, that if, okay, let's say, if these 2 points there are identified, so maybe I should take, okay, let's take these 2 points there. If these 2 points there are identified, okay, then necessarily on the other side, they should be singletons in the sorry, that's actually it's actually a mistake that I do all the time. Yes, it's actually a mistake I do all the time. So, so in fact, it's even more than that is true. I'm sorry. So, in fact, if S is different from T and dE of ST is equal to 0, then S and T are both equivalence classes for dz is equal to 0, and vice versa. Okay, so it's even stronger, if you like. Okay, it means that if DE and ST is equal to 0, if they are identified by the Brownian tree, then not only they are not identified in the tree coded by Z, but they are really leaves of this tree. Okay, they are alone in their equivalence classes. Okay, and similarly for the other side. So this now really means that if you have 2 points that are identified on this side, then on the other side, you know, there are only these points are alone in their equivalence classes. Okay, the singletons are equivalence classes, and vice versa. And if, for instance, you take this ideal triangle here, then all the points that stand below are also alone in their equivalence classes. Okay, so this means that the equivalence classes of yes. Okay, so I'm sorry, I was really careless here. Are, you know, are the union yeah, sorry. So I went really too fast in preparing this this here. You know, it's not even clear, of course, that, you know, in general, the union of two equivalence classes is of two equivalence relations is not necessarily an equivalence relation. Okay, so when I'm writing this, you know, I'm already using the proposition that was on the blackboard. Okay, and then the equivalence classes of this union are just the equivalence classes of either one of these relations. Okay? And now we apply Morse theorem. Okay, we can apply Morse theorem because we see that the equivalence class is in question, and that's the reason why we filled the triangle. Okay, when we remove any of these equivalence classes, we end up with the complement is connected because the equivalence classes are either arcs or points or you know, topological triangles. Okay, and that concludes the proof. So of course, this was not at all a complete proof, and the technical part is really to prove this proposition, okay, which is a property of stochastic processes. Okay, it's a property of the processes E and Z and how they relate to the distance d, and that requires actually a lot of work. Okay, so time is running fast, so I want to finish with this topic on scaling limits. There are really many more things to say about those. So for those of you who are interested, I really recommend, for instance, reading the Buzios lecture notes or the Saint-Flour lecture notes, which contain the further developments on these aspects. And I want maybe to finish by finish on the scaling limits by mentioning that everything that I've said, so far is really you take a combinatorial family of objects, which are maps. You sample them, you take scaling limits, and you get nice limiting metric spaces. But there is really an important question about these objects, which is can you represent them using more familiar objects? You know, the Brownian map is really a quotient of the interval 0, 1 by some weird equivalence relation, random equivalence relation. But we just saw that it's a sphere. So can you actually represent the random map as a random metric defined on the usual round sphere? Okay, and this topic is an important question. So sort of explicitly represent the Brownian map as a random metric on S2. And of course, this random metric, so everything is in the explicitly. Of course, by sort of, you can fix, for instance, a homeomorphism that is prescribed by the theorem that I just sketched the proof of, and then carry the metric of the Brownian map to the sphere. But it will be something that is completely abstract and non-explicit. Okay, and the conjecture is that this can be done using objects that you are now familiar with, like GFF and Gaussian multiplicative chaos. And this idea originates from physics. Essentially, it should be true that the metric should be a variant of something like exponential to some constant times the Gaussian free field defined on the sphere times the usual Euclidean metric on the sphere. Okay, for some constant gamma strictly positive and h a GFF. And of course, this object, as we know, GFF is the Gaussian free field is not a function; it's a distribution. So this exponential of the Gaussian free field needs interpretation. And in Rémi's lectures, you saw how to make sense of an object like e to the gamma h times dz. Okay, where dz is rather the volume measure on either the sphere or the plane. Okay, so this sort of is okay by Gaussian multiplicative chaos. But this is a rather different object. It's a random metric, if you like. So it is not known actually how to properly renormalize this object to make it sensitive, a sensitive mathematical object, a sensible mathematical object. Sorry. However, this is related to recent work by Miller and Sheffield on so-called quantum Loevner evolutions, which are supposed to describe the process of growth of balls in this metric. Okay, so it does not sort of define this metric by a renormalization procedure like for Gaussian multiplicative chaos, but it sort of uses other ideas. Okay, and this is of course one of the very important problems in nowadays study of random maps. You know, it's kind of mysterious how these very intrinsically combinatorial objects are related to conformally invariant processes like GFF. Okay, so in the last part, so I think this is number 5. We haven't had a new number for a long time, but so 5 will be on local limits of random maps, actually triangulations. And here I will take a rather different point of view from the one we have adopted so far using bijections. Although bijective techniques also have interesting consequences in this framework, in this theory, in this topic. And the ideas are actually quite similar although at a very elementary level, to ideas that, for instance, Jason has been discussed in his notes about local sets of the GFF. And it's also quite related to the way that you want to construct QLEs. Okay, so I hope that at least the simple ideas that I'm going to describe here are going to give you some intuition about these more elaborate topics. Okay, so first of all, I want to consider Boltzmann. Okay, so maybe what's the goal here? So here we want to take a triangulation. So we could also take a quadrangulation as before, but it's somehow in the way I'm going to present things, triangulations are simpler. Uniformly at random, with, say, n faces, or n vertices. Problem with triangulation is that they have an even number of faces. So let's say n vertices. And let's say it's rooted. And we want to let n go to infinity without rescaling. And the question is, do we observe an infinite random map in the limit? Okay, and of course, this will need some interpretation. Okay, in order to observe, in order to take limits of such objects, we are going to need to look at the neighborhood of a given point, for instance, the root, and see that finite, arbitrarily large but fixed neighborhoods of this fixed point stabilize as n goes to infinity. Okay. So, okay, so maybe I want to define two things. So it's so local topology on maps. So let M and M prime be two rooted maps, and I want to consider them on S2. Okay, really, all the maps are plane maps. And set D loc of M prime to be the supremum R, such that the ball of radius R in M is isomorphic to the ball of radius R in M prime. Add one and take the inverse. Okay, so where I didn't specify it, BR of M is the ball of radius R around the root vertex in M. Okay, this is again just a convention. So you have a map. For now, it does not have to be a triangulation. The root vertex is just the origin of the root edge, and then you take the combinatorial ball, meaning the ball for the graph distance, and you see it as a map. Okay, and you take the largest R such that the balls of radius R around the root of M and M prime are the same. So this tells you that if this number R is very large, then M and M prime look the same up to a very long distance. Okay, so you want to say that M and M prime are very close if this supremum is large, meaning that this inverse is very small. Okay. So proposition D loc is a distance on rooted planar maps. And I want maybe to call MF to be the set of maps, and F stands for finite. And we let M D loc be the completion of this space. And I want to interpret the points in the completion that are not in the original space as infinite maps. So we want to interpret elements of M minus MF as infinite maps. And it's actually interesting to think about in what sense these objects are indeed maps. Okay, the thing is that they can be seen as maps drawn on non-compact surfaces. And there is actually there are many more non-compact surfaces than compact surfaces. There is really a continuum of such objects. But in what we are going to be interested in, we will see that the non-compact surfaces in question will be only essentially the plane. Okay, so just the sphere minus one point. Okay, but I don't want to go too much into these details. Okay, what is really an element of the completion? If you look at the definition of the local distance, in fact, the information about a map is really given by the information of the finite balls around the root. Okay, so these elements, they can also be seen as sequences BR of finite, say, of elements of MF, such that it's really curve BR, such that the ball of radius R of the map BR plus 1 is equal to BR. Okay, in this sense, it's a consistent family of balls, and you want to interpret, the reason why I use also the letter B, is you want to interpret these BRs to be the ball of the infinite map associated with this map. And now the theorem. So let Tn be a uniform triangulation with n vertices. Then Tn converges in distribution as n goes to infinity for in M d log to a limit T infinity which can be represented in the plane without accumulation points. So, if you like, this limit is really a triangulation of the whole plane. Okay, and it's called the uniform infinite planar triangulation. And it was introduced by Angel and Schramm about 13 years ago. So I'm not going to show this theorem. Rather, I'm going to concentrate on a variant of this theorem, which involves an object that is slightly better behaved in certain ways than this object T infinity. Okay, but I cited this theorem because it's a kind of emblematic. First of all, because it was the first theorem on this topic, and second, because of course T infinity is also an object of the object of a lot of studies. Okay. Okay. So rather than T infinity, we will focus on a different model of infinite random maps. And these ones have an infinite boundary. Okay, so if you want, these maps are more maps of the half plane than the plane itself. And in order to do that, I will need a little notation. Okay, so let TR NM to be the set of triangulations of a polygon of degree n, so triangulations of an m-gon, rooted at the m-gon and with n internal vertices. Where by internal, okay, so first of all, what do I mean by a triangulation of the m-gon? So an m-gon is just a polygon with m sides, okay, and m edges. And I want the root to be always on the polygon, okay, such a way, say, that the polygon stands on the left. Okay. And further, I want to triangulate this polygon. Okay, so this polygon is really paved by a family of triangles like this. And in the counting, I'm just considering the internal vertices, which are the vertices that lie inside the polygon. Okay. So there is actually an explicit formula for this, for the number of such triangulations, and I maybe want to give it. It's a bit nastier than the formulas we've been encountering so far for triangulations, but it's not so bad. It's 2 to the n plus 1, 2m minus 3 factorial, 2m plus 3n minus 4 factorial divided by m minus 2 factorial squared n factorial 2m plus 2n minus 2 factorial. So it's a bit longish, but it's okay. And if you look at this formula, you will see that there is maybe a little problem. If you take m to be equal to 2 and n equal to 0, you will find something non-zero. Okay, but it's m equal to 2 means that you have a 2-gon. And you cannot have a triangulation without internal vertices. Okay, so in fact, you do have one. We sort of allow a single edge like that to be a part of this family. Okay, so this is the unique element of TR of 0, 2. So, and we really interpret that as a 2-gon, which is folded on itself because it has no faces inside. Okay, so I was not completely precise, in fact, here. I should also say that these triangulations, they have no self-loops. Okay, so it's possible also to enumerate those with self-loops, but the formula is not as good. Okay. Okay, so starting from these triangulations, there are sort of two ways to try to sample an infinite triangulation of the half plane, if you like. Well, the half plane, I can think it of being an m-gon with m being infinite. Okay, so one way to do things, of course, if you let m go to infinity and fix n, then after some point you have no sort of nothing interesting happens. So you have to do things either in this following way. So you want to consider T, N, M to be uniform in TR and M, and then try to get a local limit as n goes to infinity to some infinite map of the m-gon, you know, a kind of generalization of the theorem by Angel and Schramm, and then let m go to infinity and hope that in the end you get an infinite map defined on the infinite, the infinite gun. Okay, and this is something that you can do. But I'm going to use a slightly different route. So one can to take two consecutive limits. But I'm going to take a different route by introducing a somewhat nicer distribution on the set of maps with boundary, which is called Boltzmann distributions. Okay, so I'm out of time now. So okay, I'm just going to give the plan for next time. So what we are going to do is, Boltzmann distributions are going to be random maps on a fixed size boundary M-gon, okay, but in which the number of internal vertices is random. Okay, so if you like, these Boltzmann distributions, they are a bit, they are to maps the same that Galton-Watson trees are to plane trees, if you like. You know that plane trees with energies, a uniform plane tree with energies, you can also see it as a branching process, so with a random number of vertices, and condition the number of vertices to be equal to n, okay, or to n plus 1. And here we are going to do a little bit the same. And the idea behind that is that these Boltzmann distributions have a very nice branching property that will tell us a lot about the structure of the limit. Okay, but I don't have time to go more into detail here, so I'll stop here. Thank you. Any questions?
Is there any hope of extending these results to just typical random maps, so not quadrangulations?
Yeah. I didn't mention that, but there are universality results, okay, and so the most powerful somehow universality result has been obtained by Le Gall, and he showed, for instance, that uniform triangulations also converge to the Brownian map, and it uses a very nice argument. It's it uses a very nice symmetry of the Brownian map, which is the invariance under rerouting, and sort of using these techniques, you can in fact extend enormously the family of maps that also converge to the Brownian map. Okay, so a recent result that we obtained with Jérémy Bettinelli and Emmanuel Jacob is the exact analog of the statement for trees. So if you take Mn, a uniform random map rooted with energies, okay, then with the same normalization, this converges to the Brownian map. Okay, and this is the kind of results that you can attain. Here, you don't have triangulations, quadrangulations. You don't fix the degrees of the faces. You just take a map with energies. Okay, and then you have this scaling limit. And what's surprising in this fact is that the renormalization 8/9 is actually the same as for quadrangulations, which is quite surprising. It really means that the distances, the D is exactly the same as before. The normalization of the D is fixed. Okay, so it means that typical distances in a uniform random quadrangulation with n faces and in a uniform map with energies are the same, which is kind of striking. Okay, coffee break.